Gene maps are maps of chromosomes that are created based on recombination frequencies. So these maps can be constructed because there's this relationship between the recombination frequency and the distance that genes are apart from each other. So the lower the recombination frequency, as that gets smaller and smaller, then what that means is that the closer the genes are. And then we could say just the opposite: the higher the recombination frequency, the farther the genes are from each other. And so with this, a few things to remember is that we're always comparing two genes at a time. And then another thing to remember is that the recombination frequencies are never higher than 50%. And the reason for that is that, remember that 50% indicates independent assortment. So if we do get 50% for our recombination frequencies, really what that's going to tell us is that the genes are pretty much 50% of the time they're going to be separated from each other. So that means that they could be either located on different chromosomes altogether and they would assort independently, or they could be located very far apart on the same chromosome. So that would be if we get 50%. If we get less than 50%, then we know for sure that they are located on the same chromosome. So the way that this is going to work is that 1% recombination frequency is going to be equal to what we call 1 map unit. And that's abbreviated in MU. So the map units give us a relative distance of the genes as far as how far apart they happen to be. So let's look at an example of this. If we look at this particular picture, this is a chromosome map, and what it is showing us is the relative distance between these 4 different genes that we have listed here. So between A and B, if we were to do a cross and analyze the recombination frequency between those two, we would expect to get 5%. And so again, remember that 1% is going to be equal to 1 map unit. We could also look at the distance between B and C, and since we get 7 map units, we would expect that the recombination frequency would be 7%. And then between C and D, the recombination frequency, if we were to calculate it, should be 15%. If we were to look at between, say, A and C, we would just need to add up and figure out what this total distance is. And you can see that that is 12%. And we could even look between A and D and figure out the recombination frequency there. So that would be 27%. And again, all I'm doing is adding up the 5 plus the 7 plus the 15 to come up with that 27 number here. And then the only other one that we haven't listed so far would be B and D. And so between those two, we would expect a recombination frequency of 22%. So if we look at these numbers that we've now written down here, notice that 5% is the lowest, and that would be the closest together. So if we just had these numbers in front of us and we couldn't see the map at all, just based on recombination frequencies alone, we should be able to identify which 2 genes happen to be the closest together. We should also be able to identify which are the farthest apart, which would be these down here at the bottom, the A and D, because they have the greatest recombination frequency. So again, make sure that you do understand this relationship between the distance and the recombination frequency. The lower that number is, the closer together they're going to be. Another way that we could look at this is not only are they the closest together, but they are the least likely to have crossing over between them. And then the ones that are the farthest apart, those would be the most likely to have crossing over occur between them. So we could take a map like this and we could come up with the recombination frequencies. We should also be able to really work in reverse, which that would be the way that these genetic maps are typically constructed. So here we're presented with a number of recombination frequencies. We're looking at 4 different genes. We have A, B, C, and D. And so all these recombination frequencies are telling us how likely we are to get crossing over between any of these two combinations. So we ought to be able to take this information and basically construct the genetic map or the chromosome map. Now, a few things before we actually get started constructing the map. We should be able to identify the ones that are the closest together, which would be up here on the top. So those are the closest. And the reason they are the closest is because that number is the lowest of all of the percentages. And then this one down here should be the farthest apart. And then everything else, okay, we can see that we just have a range there where, again, the lower numbers, they're going to be closer together and the greater numbers are going to be farthest apart. And we should never really have numbers over 50%. So if we wanted to construct these and figure out how they are actually arranged on the chromosome, there are different approaches. I always start with the ones that are the closest together. So I'm going to start with A and B, and I'm going to draw myself a chromosome and start to order those on there. So here's my chromosome, and I'm going to go pretty much right here in the middle, and I'm going to write my A and B, and I'm going to put 12 map units between them because that is based on the 12% recombination frequency. So I put that right there in the center, and then I'm just going to put a little check mark indicating that I have used that data. Then I would go to the next highest number, but I want to make sure that it includes either the A or the B so that I can kind of compare it to what I already have on my chromosome. And so between A and C, I'm seeing 14%. And so that tells me that C is either 14 from A in this direction, or it really could be 14 from A in the other direction. And just based on the fact that I have a 14 here, I can't really say for sure where it's at. So if you wanted, you could kind of put a little C here, but we don't want to kind of finalize the position of C because it could be in either direction. So after that, I'm then going to move to my next, I'm going to go down here to this one that includes B and C because that will help me to figure out where exactly my C should be on here. So if I know that C is supposed to be 26 map units from B, that means that C could be 26 in this direction, or it could be 26 in this direction. But if it was over here, that wouldn't give me 26. So that tells me that that's not the correct C. And this one over here must be the correct C. Because if I had 14 from A right there, then I would get my 26 there for B, which is what I'm looking for. So that tells me exactly where the C ought to be. Now if I just clean this up a little bit, okay, so if I just continue on, if I look between B and D, D is going to be maybe 21 this way, or it could be 21, so this is D, 21 this direction. And again, I don't know exactly where it's at, so I'm not sure exactly which place to put my D. And then if I just look at the next information, the fact that A and D are supposed to be 33, well, if D was 33 this direction, that wouldn't work. And so if it was 33 in this direction from A, then this would be the correct position for D. So that would tell me that this is 21. And again, now I can see that I've got my 33, which I'm looking for between A and D. And then all I have to do is check this last piece of information, that C and D are actually 47 apart from each other. So if I wanted to check that, I could just add together the 14 plus the 12 plus the 21 and make sure that that total distance is going to give me the 47 that I'm looking for between C and D. We figured out the order of the genes on the chromosome, which would be C, A, B, D, or we could write it in the other order and it would be exactly the same. So that would give us our answer for this one. So notice how we just took a list of recombination frequencies and we used them to really place the genes on the chromosome in the proper order.